Hey there, Mr. Weaver here, and this is Module 11, Lesson 1, Graphing Quadratic Functions. After this lesson, you need to be able to analyze graphs of quadratic functions, graph quadratic functions by using key features and tables, and use graphing technology to analyze key features of quadratic functions. Let's learn. Analyzing graphs of quadratic functions. A second-degree polynomial, which means it has the exponent of 2, for example, x squared plus 2x minus 8, is a quadratic polynomial. Remember when we were learning to name polynomials, quadratic meant that exponent of 2. These have a related quadratic function where we have f of x equals the same polynomial. So a quadratic function is going to be written in the form y equals ax squared plus bx plus c, where a cannot be 0, because if a was 0, that would be gone and it would no longer be quadratic. Or you might see as it's written up here, f of x. When we're graphing these quadratic functions, the graph is called a parabola. And it looks like this. Parabolas are symmetric about a central line called the axis of symmetry. So here in orange, we can see our axis of symmetry. And I'm going to write an A of S. That is that dotted line right here. It doesn't actually show up on the graph. It's imaginary, but it is what cuts our parabola exactly in half. Why this is important? Every point on the parabola to the left has a corresponding point on the right of the axis of symmetry. So for example, let's say you knew this point here, and you knew the axis of symmetry was right here, well, this parabola would have a point over here that's the same distance away on both sides. And that's going to be super helpful when we are graphing our parabolas. The axis of symmetry also intersects the parabola at the vertex. So down here, we have one point that's on the axis of symmetry. That is your vertex. And the vertex is either the lowest or the highest point of the parabola. With our parabolas, we can also have two things happening with our a values. If a is greater than 0, then the parabola is going to open up, meaning if you have your graph, it looks like this, it's going to open up, and the vertex is going to be the lowest point, and that is going to be at a minimum. Or a could be less than 0. When a is less than 0, meaning it's negative, it's going to open downward, and it's going to have a maximum at the vertex. This a value also helps determine the end behavior of our quadratic functions, because if you notice, no matter what direction we're going, the end behavior of a quadratic, they are both going in the same direction. So if a is greater than 0, the end behavior, both as it decreases and increases, will be increasing. If a is less than 0, both times it's going to be decreasing. It is going downward. Example 1. Identify characteristics. Graph with x-intercept. Identify the axis of symmetry, the vertex, and the y-intercept of the graph. Then describe the end behavior. So first, the axis of symmetry is that imaginary line that is cutting it perfectly in half. It's going to go through the vertex there. So what is that line? It's always going to be x equals, and then where did it go through? -2. So here that line is that x is -2. The vertex should include this same point, so -2 for x, and then where is it for y? It would be at 8. So our vertex is at the maximum, the highest point, at -2, 8. For the y-intercept, that is the same type of y-intercept that we've seen in other functions. So where does it cross the y-axis? It crosses at 0, 4. So we would just say the y-intercept is at 4. And then because here we had a maximum, meaning a is less than 0, our end behavior is going downward both times. So as x increases or decreases, y is decreasing. Check your understanding. Identify the key features from this graph. Pause the video now and complete the check. Check your answers. First, our axis of symmetry is at 2, so we can see it right here. Going down, it would go through x equals 2. The vertex is up here at 2 and 16. The y-intercept right here at 0, 12, so 12. And then again, this is opening downward, so as it increases or decreases, y is decreasing. Let's learn graphing quadratic functions. Our first key concept here is the standard form of a quadratic function. That standard form is f of x equals ax squared plus bx plus c. When we see this, a, b, and c have to be integers, so our easy counting numbers, and a cannot be 0. B can be 0, c can be 0, just not a. So for example, we could have 3x squared minus 2x plus 9. Here, a would be 3, b would be -2, c would be +9. If we had -16x squared, a would be -16, But notice there's no x term or constant term, so b and c would both be 0. Again, as long as a is not 0, it's fine. B can be 0, c can be 0. You just won't see those parts of the equation. Our next key concept, graphing quadratic functions. So here we have 5 steps for graphing our quadratic functions. Obviously, we could just go use some graphing technology like Desmos, but let's look at how to do it without first. So our first step is going to be to find the equation of the axis of symmetry. Now, this has a specific expression that's going to be helpful. It's negative b over 2a. And since it's the axis of symmetry, it's going to be x equals. So whatever b is up here in our equation, we plug it in on top. Whatever a is in our equation, we plug it in on the bottom, multiplied by 2, divide it out, and then make it the opposite sign of whatever it was. Next, we're going to find the vertex. So the vertex goes through that axis of symmetry. So once you figure out that x value, then you can plug that back into the equation and solve for f of x or solve for y. Whatever it comes out to be, that is going to be your y coordinate. Next, you'll find the y-intercept. So that's going to be what you get when you plug in 0 for your coordinate. So 0 and then whatever that number is. Next, we're going to use our axis of symmetry to know that we have symmetrical points on each side. So if a point is a certain distance away from it on one side, we can make another point the same distance on the other side. And then last, we will make our points into a graph by connecting it with a smooth curve. Example 3, graph a quadratic function by using key features. So let's graph f of x equals x squared plus 2x minus 6. First, let's find the axis of symmetry. So we're going to use that formula, x equals negative b over 2a, to find it. A is hidden out here, it is a 1, and b is positive 2. So let's plug those in, b on top, and then 2 times 1 on the bottom. So 2 divided by 2 times 1 would be 1, and then making it negative. So our axis of symmetry is negative 1. Next, let's find the vertex. So now that we know that the x coordinate of the vertex is negative 1, let's plug that in and solve for y. So if I plug in negative 1 where x is, I'm going to calculate it out and get negative 7. So my vertex is going to be at negative 1, negative 7. And going back to our original equation, because this a value out here is positive, the graph is going to open upward. So the vertex would be a minimum. It is going to look something like this. Next, let's find the y-intercept. So that is going to be when x is equal to 0. So if we plug in 0 for x, this cancels out, we're just left with negative 6. In fact, with quadratics, this number at the end is going to be your y-intercept as long as your function here is written in standard form. So that ax squared plus bx plus c. Whatever's at the end, plus something would be a positive y-intercept, but minus something will be negative. So our y-intercept here is negative 6. Next, let's find some additional points. We can plug in any value we want for x. Let's use some smaller ones. So x is equal to 2. If we plug in 2, simplify it out, we would end up with 2. 2 squared is 4, plus 2 times 2 is 8, minus 6 is 2. So I would have another coordinate of 2, 2. My last step is to graph these points and make enough so I can connect them with a smooth curve. In general, you're going to want at least 5 points for a quadratic. The vertex should be one of them. The y-intercept should be one of them. Determine another one, and then use some symmetry to figure out a couple others. So first, our vertex, negative 1, negative 7. Our y-intercept is at 0, negative 6. And the other point we figured out, when we plug in 2, we get 2. This here is half of our parabola. So let's use some symmetry. This would be your axis of symmetry going through that vertex. So every point has to be the same amount away. So if this is 1 unit away, there must be another point here. And if this is 1, 2, 3 units away, there must be another point here. Now I can connect it with a smooth curve. And it would look something like this, where we would extend it going upward in both directions. Example 4, graph a quadratic function by using a table. Use a table of values to graph y equals 2x squared minus 8x plus 2. So really, a table is just helping us organize the same types of coordinates that we had before. So first, let's find our axis of symmetry so we can find our vertex. X equals negative b over 2a. If we plug in a and b, then we end up with 2. Careful here, b is negative 8. So I would do the negative out front and negative 8 on top. When I calculate it out, once I simplify it out, I end up with 2. So I know my axis of symmetry is going to be right here, meaning every point this way is going to be the same distance away as every point this way. And we will see a pattern in this as we fill in the table. So first, let's find our vertex. If we plug in 2 now, what are we going to come out with? So 2 times 2 to the second power minus 8 times 2 plus 2. X1 is first, so 2 squared is 4, times 2 is 8, minus 8 times 2 is 16, plus 2. 8 minus 16 is negative 8, plus 2 is negative 6. So this here is your vertex, and this is your axis of symmetry. Next, let's fill in 0, and when x is 0, that's your y-intercept, which is that number right at the end. So if we plug in 0, we get 2. Then we can complete the table. If we plug in 1, similar to how we plugged in 2 up here, we would end up with negative 4. If we plug in 3, we also get negative 4. And if we plug in 4, we get 2. Notice there is a pattern starting from the vertex or your axis of symmetry. As you go one way, it's the same number going the opposite direction. And then whatever you figure out next, it ends up being the same number again. As long as you're following a consistent pattern up top, here we're just going one way each time. So our pattern on the bottom will be symmetrical. Our y-intercept then is 0, 2. Again, that's where we saw that right here. The vertex is a minimum. How can you tell? Well, what is the y value there? If you plug it in, the values start going up. If you're not sure about the negative 4, well, 2 is definitely above it. So it would be up higher, meaning this has to be a minimum. So let's graph these points. We have 2, negative 6, 0, 2, and now here I plugged in 4, 2. If I were to graph the other two, I'd have 1 and negative 4 and 3 and negative 4. And a smooth curve through it as best as we can would look like this, where we're going upward on both ends. This parabola, as with most parabolas we're going to see, they're extending to infinity with those arrows. Our domain here, remember domain is your x values, those are all real numbers. So this is actually getting wider and wider and wider. We can plug in any number we want for x. Quadratic functions are going to have a domain of all real numbers. The range, on the other hand, is your y values, but for the range of quadratics, they don't go forever up or down. They're going to go one of the directions forever, but the other direction at some point is either going to stop going down for the minimum or going up for the maximum. So here we have a minimum, meaning the y values are all above it. And what is that minimum? It is at negative 6. So as you're going through quadratic functions, wherever the minimum value or maximum value is, that is going to be the boundary of your range. Example 5. Use the graph of a quadratic function. Our real context here is catapult. In 1304, Edward I built Warwolf, one of the largest catapults ever used in battle. It had the capacity to launch a 300-pound boulder over 900 feet. The height of a projectile launched from Warwolf can be modeled by the function h of x equals negative 16x squared plus 96x plus 40, where h of x represents the height in feet of the projectile after x seconds. Graph the function. Interpret the key features of the graph in terms of the quantities. So first, to graph this, we need to find our axis of symmetry. So we're going to plug in our values for b and a. When we simplify it out with a is negative 16 and b is 96, we end up with our axis of symmetry equation is x equals 3, meaning that our vertex is at 3 something. So let's plug in 3 to our equation and see what we come out with. We would end up with a height here, a y value of 184. So the vertex would be at 3, 184. Next, let's use our function to complete a table. So if we plug in 0, we're going to end up with 40. If we plug in 1, we would end up with 120. Plugging in 2, we'd have 168. I could keep substituting in, or I can try to follow a pattern. Remember, this here is my vertex, so going this way and going this way should follow the same pattern. 168 is 16 less than 184, so it should be back 16 less. And then down to 120, so it should be back to 120. Next, if we graph our function, here we can see our vertex at 3 seconds is up to 184. Our y-intercept here is at 0 and 40. And we could have plugged in any of these other values to help graph our smooth curve. Now that we have our graph, let's interpret some of the key features. So interpreting here is going to be a pretty important part for graphing within a context. So here we have a new one for an x-intercept. That is going to be down here where it crosses the x-axis. There's another one over here somewhere, but that would be at, like, say, -1, maybe more of a decimal. But since t is talking about seconds, we can't have negative time. We would just kind of ignore it. So our x-intercept here, 6.4. The important interpretation here means that the projectile landed about 6.4 seconds after it was launched. So we can see it went up and back down and hit the ground. So this would be essentially the ground. For the vertex, we figured out that it was up here at 3 and 184. So what does that mean? The projectile reached its maximum height of 184 feet 3 seconds after it was launched. So this is your time, this is your height. 3 seconds, it was at 184 feet. When is it increasing? Well, it's increasing until it gets to the vertex. So before h equals 3. So when x is less than 3. What does that mean? It is gaining height until 3 seconds. When is it decreasing? Well, after those 3 seconds. So when x is more than 3. So it's falling 3 seconds after launch. Other characteristics, this one is always positive. So it's where the projectile is in flight. This one has to be always positive because you would be saying that the projectile went below ground. Unless, of course, that's what you're intending. But here we're saying it hit the ground. So it is always going to be positive. Our end behavior, as it goes each direction, it represents the projectile starting and then returning to the ground. Your domain, here, with just a basic quadratic domain will be all real numbers, but here the domain is just your x values. It started at 0, and the projectile was done flying through the air at 6.4. So your x values only go between 0 and 6.4, so it's the non-negative numbers less than 6.4. And then your range, the lowest it's going is the ground. What's the highest it's going to go? 184. So the range would be between 0 and 184. Example 6. Interpret the graph of a quadratic function. Our real context here is horses. In 1949, Hueso, I think I'm saying that right, written by Alberto, and I'm not even going to try to pronounce his other names, set the world record for the highest jump by a horse when he cleared a 2.47 meter high obstacle. His path can be approximately modeled by f of x equals negative 0.418x squared plus 2.033x, where f of x is the height above the ground in meters and x is the distance from the point of takeoff in meters. Find and interpret the key features of the path of Hueso's jump. So first, let's graph the function. Here I used Desmos to make a graph. I just went to Desmos, typed this in, and it graphs it for us. So the graph here exists only in quadrant 1, meaning we really should just cut it off here because we can't go negative for time and the horse is not jumping below ground, so we're only existing in the positive quadrant. So let's find the vertex. If we go here, the vertex is that maximum point. In Desmos, you can click on the vertex. It is located about 2.43 and 2.47. So at 2.43 seconds, it was 2.47 meters tall. So this represents that the height is 2.47 when he was about 2.43 meters from his point of takeoff. Be careful here. This is not saying the number of seconds on this one. Again, x is the distance from the point of takeoff. So be careful in the context that we are keeping that in mind. Step 3, find the axis of symmetry. Well, we just saw that the vertex was at 2.43 and 2.47. So what was the x value there? 2.43. This means that Hueso's path before he hit 2.43 is the same after he reaches 2.43. So those heights here will be the same before and after. They're the same distance away and the same height of that 2.43. Next, let's find the y-intercept. Down here at 0, 0. The y-intercept is 0. This means that when he took off, he was 0 meters high and 0 meters from the point of takeoff because that's where he took off. He wasn't any distance away from it. Step 5, find the zeros. Now we haven't seen this yet in this chapter, finding the zeros, but the zeros are just your x-intercepts. So where are your x-intercepts? There's one there, there's one there. They are located at x equals 0 and x equals 4.86. Again, in Desmos, you can actually click on those dots so you don't have to guess. These two numbers represents the point of takeoff. So here's where he took off. Here is where he landed. So we can tell that's where they took off and landed because his height was at 0, meaning he's on the ground. And then the end behavior, from that maximum value, we are decreasing. So the y value is decreasing until it reaches 0. Again, these are representing his taking off and his returning to the ground. If we head over to Desmos, here I copied and pasted. Notice it doesn't look like it should because when you copy and paste into Desmos, you need to make this into an exponent. It doesn't like that. So if we change it to an exponent now, we can see the correct parabola. So here I can see my x-intercept and y-intercept because it's at 0 and 0. I can click on my vertex, 2.43, 2.47, and then we can see it goes back down, hits the ground again at 4.86 foot. So you can actually just click on these points. If for whatever reason, maybe the horse took off from 2 meters above the ground, so at +2, we can see that our values changed slightly because he started slightly higher above the ground. So our y-intercept has changed. Our x value actually didn't change for the vertex, the y-axis, for the axis of symmetry, but its height is now at 4.47. So the height got a little bit higher. We can also see that it took a little bit longer to hit the ground, and there is now another 0 over here at negative 0.83, but this would be like the horse going back in time. So if this showed up the way it was, we would just ignore that other 0. So you can use Desmos to help find these features when you plot them in. Your key part is going to be knowing how to interpret them in the context.